When we talk about AI-driven climate technology, we are really discussing the application of advanced computational models to one of the most complex, nonlinear, and high-stakes systems humanity has ever tried to understand and influence. Climate is not a single system but a tightly coupled interaction of atmospheric physics, ocean dynamics, land processes, biosphere feedback loops, and human activity. Traditional modeling approaches, while grounded in first principles physics, often struggle with resolution limits, computational cost, and uncertainty propagation. AI introduces a complementary paradigm that allows us to learn patterns from massive datasets, approximate complex processes, and accelerate simulation and decision-making in ways that were previously infeasible. To appreciate the role of AI in this domain, it is useful to understand how climate modeling has evolved. General circulation models, which are the backbone of climate science, discretize the Earth into grids and solve physical equations governing fluid dynamics, radiation, and thermodynamics. These models are highly accurate at large scales but face challenges at smaller scales, such as cloud formation, turbulence, and localized weather events. These subgrid processes are often parameterized, meaning they are approximated using simplified assumptions. AI models, particularly deep neural networks, can learn these complex relationships directly from observational and simulation data, providing more accurate and computationally efficient approximations. One of the most promising approaches is the integration of hybrid models that combine physics-based simulations with machine learning components. In such systems, AI does not replace physical laws but augments them. For example, a neural network can be trained to emulate computationally expensive components of a climate model, such as radiative transfer or cloud microphysics, significantly reducing simulation time while maintaining accuracy. This enables higher resolution simulations and more extensive scenario analysis, which are critical for understanding regional climate impacts. Beyond simulation, AI plays a crucial role in prediction. Climate and weather forecasting involve analyzing vast amounts of historical and real-time data from satellites, sensors, and observational networks. Machine learning models can detect patterns and correlations that are difficult to capture with traditional methods. This has led to improvements in short-term weather forecasting, seasonal predictions, and even long-term climate projections. Importantly, AI can also quantify uncertainty, providing probabilistic forecasts that are essential for risk assessment and decision-making. Mitigation is another area where AI-driven climate technology is making a significant impact. Reducing greenhouse gas emissions requires optimizing complex systems across energy, transportation, industry, and agriculture. AI can analyze these systems at multiple scales, identifying inefficiencies and suggesting interventions. In the context of smart grids, for instance, AI models can predict energy demand, optimize generation from renewable sources, and manage storage systems. This is particularly important because renewable energy sources such as solar and wind are inherently variable. AI enables more efficient integration of these sources into the grid, reducing reliance on fossil fuels and improving overall system stability. Carbon capture and storage is another critical component of mitigation strategies. Designing efficient carbon capture systems involves understanding chemical processes, material properties, and operational conditions. AI can accelerate the discovery of new materials for carbon capture by predicting their properties and performance. It can also optimize the operation of capture systems, adjusting parameters in real time to maximize efficiency and minimize cost. This combination of materials discovery and process optimization has the potential to make carbon capture more scalable and economically viable. Adaptation, which involves adjusting systems and practices to minimize the impact of climate change, is equally important. AI can support adaptation by providing detailed, localized insights into climate risks. For example, in agriculture, AI-driven models can analyze soil conditions, weather patterns, and crop characteristics to enable precision farming. Farmers can make data-driven decisions about planting, irrigation, fertilization, and harvesting, improving yields while reducing resource use. This is particularly important in regions that are vulnerable to changing climate conditions, where traditional practices may no longer be effective. Disaster forecasting and response is another domain where AI is having a transformative effect. Extreme weather events such as hurricanes, floods, wildfires, and heat waves are becoming more frequent and intense due to climate change. AI models can analyze real-time data from satellites, drones, and ground sensors to predict the wukuhun and trajectory of these events with greater accuracy. Early warning systems powered by AI can provide critical time for evacuation and preparation, potentially saving lives and reducing economic losses. Additionally, AI can assist in post-disaster response by analyzing damage, optimizing resource allocation, and coordinating relief efforts. A particularly interesting aspect of AI-driven climate technology is the use of digital twins. A digital twin is a virtual representation of a physical system that can be used for simulation, analysis, and optimization. In the context of climate, digital twins of cities, ecosystems, or even the entire planet can be created by integrating data from multiple sources. These models can simulate the impact of different interventions, such as changes in infrastructure, land use, or policy, allowing decision makers to explore scenarios and evaluate trade-offs before implementing real-world changes. However, the application of AI in climate science is not without challenges. One of the primary concerns is data quality and availability. While there is a vast amount of climate-related data, it is often unevenly distributed, with some regions having dense observational networks and others having very limited coverage. This can introduce biases into AI models and affect their generalization. Addressing this requires not only better data collection but also methods for handling missing or uncertain data. Another challenge is the interpretability of AI models. Climate science is a domain where understanding the underlying mechanisms is as important as making accurate predictions. Black box models that provide little insight into how they arrive at their conclusions can be difficult to trust and validate. There is ongoing research into developing interpretable AI models that can provide both accurate predictions and meaningful explanations. Computational cost is also a consideration. While AI can reduce the cost of certain simulations, training large models and processing massive datasets requires significant computational resources. This raises questions about the environmental impact of AI itself, as data centers consume energy and contribute to emissions. Balancing the benefits of AI-driven climate solutions with their own carbon footprint is an important consideration. Ethical and governance issues also play a role. Decisions about climate mitigation and adaptation often involve trade-offs that affect different populations in different ways. AI systems must be designed and deployed in a way that is fair, transparent, and inclusive. This includes ensuring that vulnerable communities are not disproportionately affected and that the benefits of AI-driven solutions are widely shared. Looking toward the future, it is likely that AI will become increasingly integrated into all aspects of climate science and policy. By 2030, we can expect more advanced hybrid models that combine physics and machine learning, more comprehensive digital twins, and more sophisticated decision support systems. These tools will enable more proactive and informed responses to climate challenges, shifting from reactive to anticipatory strategies. At the same time, the success of AI-driven climate technology will depend on collaboration across disciplines and sectors. Climate change is a global problem that requires coordinated action from governments, industry, academia, and civil society. AI can provide powerful tools, but it is ultimately human decisions that will determine how these tools are used. In this context, AI should be seen not as a silver bullet but as an amplifier of human capability. It can help us understand complex systems, explore possible futures, and design effective interventions. But it also requires careful stewardship to ensure that it is used responsibly and effectively. The combination of advanced modeling, real-time data analysis, and intelligent decision-making has the potential to significantly enhance our ability to address climate change, but realizing this potential will require sustained effort, innovation, and collaboration. What makes this moment particularly significant is that we now have the computational power, data infrastructure, and algorithmic sophistication to tackle problems that were previously beyond reach. The integration of AI into climate technology represents a shift toward a more data-driven, adaptive, and responsive approach to managing the Earth's systems. It is an opportunity to not only mitigate the impacts of climate change but also to rethink how we design and operate the systems that underpin our society. In conclusion, AI-driven climate technology represents a convergence of advanced computation and environmental science that has the potential to transform how we predict, mitigate, and adapt to climate change. From improving the accuracy of climate models and optimizing energy systems to enabling precision agriculture and enhancing disaster response, the applications are both diverse and impactful. While challenges remain, the trajectory suggests that AI will play an increasingly central role in shaping a more sustainable and resilient future.